Last topic of the unit, we want to talk about satellites. A satellite is anything that orbits around something else. But we are usually talking about satellites that orbit around something else because of a specific force. That would be gravity. There are two types of satellites. There's natural satellites, there's artificial satellites. Natural satellites are satellites that orbit around something else because of gravity, and they're there because God put them there. Artificial satellites are satellites that orbit around something else because of gravity, because we put them there. An example of that would be the International Space Station, right? It continues to orbit around the surface of the Earth at an altitude of about 400 kilometers. We put it there. We built it. Human beings built it. A partnership of several countries put this thing together in pieces, in space. It's now livable. Orbits around the Earth. It's a satellite, but it's artificial because we made it, versus the moon, which is a natural satellite of the Earth because it's there because of nature. You guys know that the International Space Station orbits around the Earth several times per day, and it takes different flight paths depending upon the time of, like the time of day, time of the week, whatever. There's different flight paths. So sometimes there'll be a flight path that'll orbit at the International Space Station right above Calgary. And we can see it when it orbits above Calgary. We can look on a website, a NASA website. It'll tell us exactly when to look, exactly where to look for this artificial satellite that orbits around the Earth several times per day. The website is spotthestation.nasa.gov. You just look up whatever city you want, whatever major city you want. Okay, we'll look up Calgary right here. When we do that, we're going to see that. Let's scroll down here. It is May 17th. There is, tonight, you're not going to see a very good viewing of it tonight because of the clouds up in the sky, right, because of the rain. But tonight at, well, actually, it already happened, I guess, 2:22 a.m. this morning, 3:56 a.m. this morning, there was a 6-minute viewing, although it was very low on the horizon, 10 degrees above the horizon. That's not particularly easy to see. The one at 2:22 would have been easier to see because it's way high up in the sky, 75 degrees above the horizon, but it would have only lasted for about 3 minutes. Okay, if we had this morning, the skies had been clear, we had looked up at an angle of 75 degrees above the horizon in the southwest that way, we would have saw for 3 minutes it crossing the sky like this very, very bright light crossing the sky, and it would have set above the east. So it would have went all the way across the sky, setting at 11 degrees above the horizon in the east. You would have saw it, assuming clear skies, you would have saw it plain as day. You wouldn't have saw the windows, you wouldn't have saw an astronaut waving outside, but what you would have saw is this bright light, which is effectively like a moon, right? The moon reflects light from the sun, that's why it's so bright. The International Space Station reflects light from the sun, and that's why it's so bright. The fact that it's so close is what makes it the brightest thing, other than the moon, the brightest thing in the sky. Okay, you look this website up, I'm telling you, you look it up and find a good sighting on a clear day, look in the right place, you will see it plain as day. You'll know exactly what you're finding when you see it. Okay, you don't have to be wondering like, oh, is that what I'm supposed to see or not? Okay, if you think it is what you're supposed to see. If you're wondering, oh, maybe that's not what I'm supposed to be looking at, it's not. Okay, it's plain as day what you're supposed to be looking at. So that's an example of an artificial satellite. But of course we have natural satellites as well, the moon around the Earth around the sun. Whether we're talking about natural or artificial, most satellites are going to travel pretty much in circular orbits. We know the Earth maintains an elliptical orbit around the sun, right? But it's pretty close to circular, actually, almost circular. Held in place by gravity. The Earth goes around the sun because of the sun's gravitational field. Because it goes in a circle, more or less, and because it's held in place by gravity, the gravitational force supplies the centripetal force. What we end up doing is setting those two forces equal to each other. Fc is equal to Fg. Centripetal force equals gravitational force. Now, the centripetal force is mv squared over r. This gets a tiny bit confusing, but only for a moment. The gravitational force is g m1 m2 over r squared. We got good news here. R appears in both equations on both sides, so we can cancel out one of the R's on both sides. What about M? We got M, we got M1, we got M2. It's just a difference in rotation. This would be the mass of the satellite. Agree? Like mv squared over r is going to be the mass of the thing that's doing the orbiting, not the central body. The Earth is the central body if we're talking about a satellite around the Earth. The Sun is the central body if we're talking about something orbiting around the Sun. That's not what we're talking about here. This is the mass of the satellite. M1, well, we'll say that's the mass of the producer, and M2 will be the mass of the satellite. So in the first equation, it's only the mass of the satellite. In the second equation, it's the mass of the central body. Let's change that actually from the mass of the producer to the mass of the central body, the thing that's being orbited around. M2 would be the mass of the satellite. We can cancel out the mass of the satellite as well. So what are we left with here now? V squared is equal to g times the mass of the central body divided by r. That's it. The speed of a satellite is equal to g times the mass of the central body, the thing being orbited around, divided by r. What does r stand for? Yeah, radius. What radius, though? What distance? What radius? From the center of the central body to the center of the satellite, right? A lot of times the satellite doesn't really have a big radius, so it doesn't really matter. But if you're talking about a moon orbiting around the Earth, you need the distance from the center of the Earth to the center of the moon. Talking about the space station, it's so small it doesn't really matter, but the moon isn't, so it does matter. Now, we're going to leave the equation like this because this makes it a little bit more versatile. We can rearrange for whatever we want to solve for. I'm going to star this because it does not appear on your data sheet. How come? Well, it doesn't appear on your data sheet because we want you to understand how a satellite works. We want you to understand that because it's something moving in a circle, it experiences a centripetal force, and that is caused by gravity. We want you to do the work that I just did. So remember, this is what you're going to get, but remember, you need to be able to get there because the final product is not on your data sheet. First example says Earth's moon is 3.844 times 10 to the 5 kilometers from the Earth. Now notice they give me a nice picture here. That's from the center of the Earth to the center of the moon. That's a big deal, right? Because if it's from the surface to the surface, we would have to add the radius of the Earth and the radius of the moon to that to get center to center. But because we're given from the center of the Earth to the center of the moon, we're good to go. We don't have to add any numbers in there. We want to find the orbital speed of the moon. How fast is the moon moving? We're going to say Fc equals Fg. We're going to say m, mass of satellite, times v squared over r equals g times m of the central body times the mass of the satellite over r squared. One of the r's on both sides cancels. So does the mass of the satellite cancel. We're left with v squared is equal to g times the mass of the central body over r. Solve for v. Want to solve for v here, right? Let's just square root the right-hand side. So what are we going to do here? 6.67 times 10 to the minus 11. The mass of the central body is what? The moon of the Earth? Earth? Yeah, Earth. 5.97 times 10 to the 24. Divided by r, which is 3.844 times 10 to the 5. Is that right? No? Mackenzie, what's wrong? Not in meters. We've got to convert that. We're going to multiply by 1,000, or 3.844 times 10 to the 8. Now notice we don't square that because we canceled out one of the r's. Let's figure out what that is now. 6.67 times 10 to the minus 11 times 5.97 times 10 to the 24 divided by 3. Oh, watch this. 3.844 times 10 to the 8. This is the perfect example of what I was telling you earlier and how to enter numbers into a calculator, right? I'm not squaring the bottom there. I could just enter it like this without brackets. Okay, if I enter it as 3.844 times 10 to that hat button, right, this button right here, then that's going to give you the wrong answer. So I'm going to press enter there. I'm going to press square root, and Josh will get your question in 1 second here. We get 1,017. That means the moon is orbiting around at 1.02 times 10 to the 3 meters per second. The moon is orbiting around the Earth at over 1,000 meters per second, over 3,600 kilometers per hour. Now remember, the speed is going to change a little bit because the orbit is slightly elliptical, and the closer it gets to the central body, the faster it's going to go. But it's close, right? It's on average, it's going to be this speed. Josh, you had a question? You good? Have a look, please, for homework at these two questions on page 278.